Hi, welcome back to Discovering Patterns in the Microbiome. In this video, we will continue discussing supervised learning, including an application of random forests. Now, in the last video, we were discussing how to do cross-validation and how if you're doing lots of tuning of your model, but you don't have a big data set, you really need to do a nested cross-validation where you do one internal cross-validation to train your model, and then you evaluate it on some extra held out data. Then you put that data back in, pull out some other data as the test data, and retrain, and so on. However, there are cases when it's okay to just report the cross-validation error without doing nested cross-validation, and that's when you're not doing any tuning to improve the model. So you're training the model, but you're not, say, trying 100 different values of some threshold that changes how your model behaves. You're just taking the vanilla flavored version of the model and running it on the training data and testing it. So in that case, you can just use regular cross-validation, and supervised learning script in QIIME is using the random forest classifier, which by default does not do any tuning. So here, it's actually okay to just run this script and report the cross-validation error. But what you don't want to do is say, try rerunning your data with a whole bunch of different processing parameters like different thresholds for removing rare taxa and picking the lowest cross-validation error. So I'm going to give you a brief overview of the random forests classifier. I evaluated this a few years ago and compared it to a number of different methods and found that it was pretty consistently the best performer, or at least tied for best across different tasks. And that's more or less held up over the years. So what a random forest is it's a forest, we say, of decision trees. And each decision tree is trained on a subset of the data, and then the trees vote for the correct class in classification. So what is a decision tree? Well, here's a picture of some decision trees. So you can see the tree has a bunch of different nodes. At each node, it's doing a comparison, which might be OTU 5 is greater than 0.4. And if so, then go to this decision path, otherwise go to that decision path. And so when you get a new sample and you want to run it through this decision tree, you would just ask these questions. Is OTU 5 greater than 0.4? Is yes. Is OTU 11 greater than 5? No. Then let's classify it as class A versus class B. Decision trees are very easy to understand. You can just look at them and see how they're doing the classification, but they tend to be very unstable. If you perturb the data a little bit, the trees don't work as well. So what random forest does is it takes a subset of the data, about 2/3, and a subset of the features, which is it's usually the square root of the number of features, and then it trains a decision tree. It's kind of a noisy, poorly trained decision tree. Kind of funny to actually throw out some of the data. But then it takes a different random subset of the samples and a different random subset of the features and trains another decision tree, and then another decision tree. And it does this for 500 or 1,000 decision trees. And what happens is, although every one of them on its own is a very poor classifier, when you have them all vote for the correct class, their errors tend to cancel each other out. And so what you're doing is more or less averaging over all of the different decision trees that would come when you try different sets of samples and different sets of features for the training. So there are a number of nice features that random forest has. One of them is that you can, when you train it, you can easily also estimate its accuracy. And here you don't even have to do cross-validation. It's called out-of-bag error. And what it does is, if you want to, let's say you've got a bunch of training data, you want to estimate how well random forest is going to predict new data. So what you do is you go to, let's say you want to predict this one sample. You go to just the decision trees that never had that sample in their training data and let them predict that sample. And so, because each tree is only built with about 2/3 of the data, it gets to predict the other third of the data. And you just average the performance of all of the trees for predicting only the samples it didn't see during its training, and you get a good error estimate. This is called the out-of-bag error estimate. You can also do cross-validation with random forests, where you take out a piece of the data, run the training on the other 90%, say, and predict the held out data, then put it back in, take out a different 10%, and so on. So you can do that too, and that's also built into QIIME. Now, I mentioned that I had compared random forest to a number of different classifiers back in 2010, 2011. And what we found was that the error of random forest was consistently the lowest or nearly the lowest across all of the classification tasks, even when compared to these and a bunch of other classifiers. Here's how you might actually use this in QIIME. It's pretty simple. It's the supervised learning.py script. You input the OTU table, you give it a mapping file, and then you tell it the name of the column in the mapping file that you're trying to learn a classifier for. So for example, if we're working with the global gut data, we might give it country, which is Malawi, Venezuela, or USA, and ask it to learn a classifier of which country someone's from based on their OTUs. When you run it, you're actually going to get several different files out, and here I'm going to show you what's in some of these files. So one of the files is called summary.txt, which is just a summary of the results. And here's what it looks like. So you get back this file that tells you what model was used, random forests, what error estimation type. This was using out of bag, although you could just tell it to use cross-validation as well. And the estimated error is this. So is this good or bad? Well, the best error rate would be 0, and the worst error rate would be 1. So this is actually pretty good. This means the model has 96.6% accuracy, or 3.4% error. And one thing that I like to do when evaluating how well a model is performing is compare it to the baseline error. And the reason I'm doing this is because if you have an imbalanced data set where, say, 90% of all of the samples are from people in the USA, then a really dumb classifier could just say, let's just call every sample USA, and we'll get 90% of them right, and therefore have 10% error. So what you want to see here, so that's the random guessing version. What you want to see here is that the error you actually observed, the predictive error, is much lower than the baseline error that a really dumb model that always guessed the majority class would get. And here, so it actually provides this to you here. It shows you the ratio of the baseline error to the observed error. And here, the ratio is 19. So the estimated error of random forests is 19 times lower than the baseline error for a naive model. So that's really good. I would even take something that had a ratio of the baseline error to the observed error of 2, because that means your error rate is twice as good as the baseline error. And then here it tells you how many trees were used in the random forests. The performance doesn't tend to change too much once you get it beyond 500 or 1,000 trees. The next file that I want to look at is CVprobabilities. So we can actually look at this one in Excel or a spreadsheet viewer. And here's what it looks like. The first column has the sample IDs, and then the remaining columns show the probability estimated by the model, in this case random forest, that that sample came from one of those classes. So here's a sample, AMZ C9 adult F, so that's AMZ stands for Amazonian, and so these are from Venezuela. And you see here that the model thought there was a 67% chance that it came from Venezuela, a 32% chance that it came from Malawi, and a 1% chance that it came from the USA. And it continues like this. Here's one that was a little bit trickier for the model. So you can actually see which samples were hard for it to classify. And this might be interesting to you if you want to, say, remove those samples from the analysis, or just examine what taxa are in them to find out why it was hard to classify. So here's one, AMZ 33ELD. We have 47 or 48% from Venezuela, 44% from Malawi. So it was classified correctly, but just barely. That might be a case where you would say, okay, if the probability of being in one class is less than 50%, if it doesn't have a majority probability, I'm just going to not report the prediction for that sample. And you can also find samples that it got wrong here and find out in which way it got it wrong. So, so you probably find that the misclassifications are between Malawi and Venezuela rather than between the USA and one of the developing countries. So it's important to remember that in this file, the estimates for the sample are always predicted by a model that didn't contain that sample in its training set. So if you want to plot these, report them in the paper, that's totally legitimate. The next one I want to talk about is feature importance scores. So this file gives you the estimates of the importance of each feature. So this could be your OTUs, it could be taxa, it could be genes. The importance is measured as the average decrease in the accuracy of the model when you scramble the values of a particular feature. And there's really no accepted threshold for deciding what level of feature importance is valid. Some ballpark thresholds. I tend to think of features that have an importance score of at least 0.1% or 0.001 as being moderately discriminative, and features that have feature importance score of 1% or higher of being highly discriminative. So let's take a look at an example here. I have the feature importance scores open in Excel. And what it's showing you is in the first column, these are the actual IDs of the OTUs. If you had run this on a taxon summary table, like a genus level taxon summary, there would be the genus names here. Then this column is the feature importance score. So it's the mean decrease in the accuracy of the model when you remove that feature. And here we see that this particular OTU, 205408, whatever that is, when you scramble that feature, the accuracy of the entire model tends to go down by 2%. So that's a pretty big effect of that one feature on the accuracy of the model. Then there are a few more above the 1%. So I would call all of these above 1% highly predictive or highly discriminative. Then there are a whole bunch of others that are above 0.01% that you might call moderately discriminative. Although, as I said, there's no real set threshold for this. There are a few other files that come out of the supervised learning, and they're all described here on this website. So if you're interested in digging into them, I recommend that you go there. Now, the last thing I wanted to discuss is how we're going to deal with the hardest data sets and what is left for future work, at least at the moment, in supervised learning for the microbiome. So the models that I showed so far are generic in that they don't know anything about microbiomes. They have to relearn on every training data set all of the dependencies between the features. One of the common ways to improve machine learning methods for a particular application is to make sure that they take advantage of domain knowledge or something specific we know about the type of data. So in actuality, there is some domain knowledge that's being used to choose to use random forest in the first place, because we know that random forest is good with lots of noisy features, and it's good at modeling nonlinear relationships, and it can also account for dependencies between the features like exclusive OR and things like that. So, so random forests might be good for those reasons for the microbiome, but it's not taking into account explicitly things like phylogenetic information about the OTUs. So, so I'm going to give just an example of one way in which we might be able to make better classifiers by incorporating the phylogenetic information that relates OTUs to each other. So the way we might do this is by using the phylogenetic tree to collapse OTUs at different levels. You could think of it as going back in time evolutionarily. So at the tips of the tree, we have many features, and they're very specific. And then as you go back in time, you have a smaller number of features, and they become more general. And to some extent, functionality is conserved as you go back into the tree. So here's an example on a toy data set where we have 4 different species, 4 different samples, and this is the phylogenetic tree that relates the samples to each other. So we could use these features on their own and put them into a supervised classifier, or we could cut the tree a little bit farther back in evolutionary history and bin them. So species 1 and 2 would get added together and become a new feature, and then species 3 and 4 would get added together and become a new feature. And then this may actually improve our accuracy. So this would be one way of adjusting the complexity of the model. As you go farther and farther toward the tips of the tree, the models are more complex. And as you go farther and farther back in the tree, the models are more simple. I did a little bit of evaluation of how well this would work by using the tightness of sequence clusters as a proxy for using the phylogeny. So we've already discussed OTU picking and how to deal with sequencing error and small amounts of evolutionary divergence of the 16S gene. We often cluster sequences together at 97%. So this takes us from 100 million sequences down to, say, a few thousand clusters. And what I wanted to find out was, if you vary the tightness of the clusters from very broad clusters of 70% similarity all the way up to very specific clusters of 99 or 99.5% similarity, what happens to your classification accuracy? So at the one end, with very general clusters, you'd only get a few, like say two clusters. This would be like clustering at the kingdom level. As you increase the tightness of the clusters, you get more and more features. So at 99% similarity, you might have 1,000 OTUs. At 99.5% similarity, you might have 5,000 OTUs. And what we're interested in finding out is the shape of the curve of the prediction error. Before I ran this, I put forth several different hypotheses about the shape of the prediction error curves. The first one is what I call the 97% hypothesis, which says that error gets better and better and better as the clusters get tighter and tighter and tighter until you get to 97% clusters. And then when you go past that, the error gets worse. And everyone would be very happy if this was the best model, because we've all been clustering our OTUs at 97% for the last 10 years. But it sounds a little too good to be true. There's also the more is better hypothesis, which shows that, which proposes that the error just keeps decreasing, that clustering is a bad thing. The more specificity you have, the better. And then finally, there's the alternative hypothesis, and this is what I expected, which is that every classification task has a different sweet spot somewhere in the middle where the models aren't too simple nor too complex. And now I'll show you applications of this to several different data sets. So one is body habitat, and this is one that we looked at in the previous video. And here we see that the best accuracy, or the lowest error, comes right about at 97%. The next one is forensic identification. So this is telling what person a sample came from. And here we get this weird dip in error out, say, at the phylum level. And then again, but then it just keeps getting better and better and better as you go down toward species or strain level resolution. And this makes sense because we know that people tend to have their own personalized strains living on them. Finally, I applied this to a lean versus obese data set and found that the best classification error was somewhere in the middle, right at about 82% similarity. And this was interesting because normally nobody would dream of clustering their OTUs at 82% similarity because it would seem like the features are too broad to be useful. But for something like obesity, they actually are better classifiers than trying to go all the way down to the species level. And just to give you something to think about, the optimal features would probably be not just one threshold across the whole tree of life, but really some kind of arbitrary cut across the tree that gives you specificity in certain regions of the tree or certain lineages where it matters for that classification task. And then it zooms out in other regions where you only care about genus or family level differences. In summary, you can use the supervised learning script in QIIME. It makes it very easy to run the random forest classifier. And it will report either the out-of-bag error estimate, or you can have it do cross-validation. Either one is fine. We have only been discussing classification, but there are cases where you may want to do regression. So you don't just have two categories, but you have a continuous variable that you want to regress on the data, like, say, BMI. Those are still under active development. Then finally, I talked about how optimal feature selection is going to need to take into account phylogenetic or functional relationships between the OTUs.